If you've worked on any slightly complex C++ projects, you must have struggled with this question. When this function fails, how exactly should I report the error? Return an error code? Throw an exception? Or just terminate outright? The most frustrating part is that all three approaches are actually valid in C++. But on second thought, none are perfect. Today, we're going to get to the bottom of this confusing issue that plagues countless C++ developers. What pitfalls exist in different error handling methods? And why is C++ error handling still so messy to this day? The earliest and simplest error handling method in C++ is the error code. For example, the most familiar file operation function for all of us typically looks like this on the screen. The return value of the function directly indicates success or failure, and the caller must check the return value themselves. Objectively speaking, the fact that error codes have been used to this day certainly means they have their merits. Firstly, their behavior is completely predictable with no black box logic. Secondly, they don't rely on any runtime mechanisms, resulting in extremely low performance overhead. Thirdly, they are safe for cross-module and even cross-language calls. That's why operating system interfaces, low-level libraries, and core performance-sensitive codes still almost all use error codes. After all, in these scenarios, stability and performance take priority. But error codes have their problems too. First of all, they're too easy to ignore. Many people casually write open file function. When coding, then move on directly, completely forgetting to check the return value. Second, they pollute the control flow. If there are many nested function calls, you have to check error codes layer by layer. The code will soon turn into a pyramid structure with indents piling up, making it extremely unreadable and a maintenance nightmare later on. And the most fatal issue is the third one. Error codes easily leave objects in a half-failed state. For example, when writing a function to initialize an object, it may apply for some resources and execute part of the logic, but then fail at a certain step and return an error code. At this point, the caller has no idea which resources have been successfully applied for. Is this object still usable now? How to clean up afterwards? This can easily lead to resource leaks or logical errors. Precisely because error codes have so many pitfalls, C++ later introduced exception mechanisms. From a language design perspective, exceptions are actually an extremely elegant solution. It allows developers to focus solely on describing the logic of the success path, while failure cases propagate upward automatically through exceptions. No need for manual layer-by-layer checks. Meanwhile, when combined with RAII, resource acquisition is initialization, exceptions ensure safe resource recycling. Even if an exception is thrown halfway, the destructors of local objects will be called automatically, preventing resource leaks. In addition, constructors can also indicate failure by throwing exceptions, unlike error codes, which require an additional initialization success flag. Semantically speaking, exceptions are almost perfect. But ideals are full, while reality is harsh. All problems with exceptions lie in engineering practice. First, exceptions are not free. To support exceptions, compilers need to generate additional information. The stack unwinding process is unpredictable, and it's difficult to accurately locate bottlenecks during subsequent performance analysis. Second, it's extremely difficult to use them uniformly in engineering. Have you ever encountered a situation like this? The library in your team uses exceptions for error handling, but the application layer code disables exceptions. Or vice versa. The application layer throws exceptions, but the low-level library doesn't handle them. In the end, everyone has to guess when writing code. Can I throw an exception here? Do I need to catch it here? No one can give a definite answer, leading to extremely high communication costs. And the core reason many teams directly disable exceptions is the third problem. Exceptions are extremely risky when crossing modules or boundaries. If the exception agreement between modules is unclear, for example, one module throws a certain type of exception that another module doesn't anticipate or handle, the program will crash directly, making graceful failure impossible. Let me add a note here. In fact, there are 3 exception safety levels in C++: basic guarantee, strong guarantee, and no-throw guarantee. Understanding these 3 levels can reduce the risk of using exceptions within a module, but the cross-module problem remains difficult to solve, since both error codes and exceptions have pitfalls. After C++ 17, the standard library has provided us with some more modern-looking tools, such as std optional, std variant, and std expected, which was officially included in the standard in C23. Let's correct a common misunderstanding here. Many people think std expected is from C++ 17, but in fact it wasn't officially part of the standard until C++ 23. Before that, it was mainly used through third-party libraries like Boost. The core idea of these tools is simple: make errors part of the type system. The caller must explicitly handle errors, otherwise the code won't compile, avoiding the problem of forgetting to check for errors at the source. Doesn't that sound perfect? But after using them for a while, you'll find that essentially they're still more elegant error codes. You still need to pass error information layer by layer, manually check for success, and decide how to combine multiple errors on your own. The only change is that the syntax is more elegant and the code looks more modern, but the core complexity of error handling hasn't disappeared. After talking about these mainstream methods, let's discuss a commonly misunderstood keyword, noexcept. Many people think that functions marked noexcept are faster and safer, but that's not the case at all. The true meaning of noexcept is, this function promises to the compiler and caller that it will never throw an exception. If you break this promise and an exception is thrown in the function, the result won't be an error return, but the program will terminate directly. This is more drastic than an exception crash with no chance of recovery. So in the context of error handling, noexcept is not a solution, but rather a risk amplifier. It requires you to have absolute control over the code, knowing exactly where failures are impossible and which failures are unrecoverable. Of course, that doesn't mean noexcept is completely useless. For example, if you mark a container's move constructor as noexcept, the container will choose a more efficient move operation instead of copying during expansion, resulting in better performance. So its value is scenario specific, not absolutely useless. Now the core question arises, why is C++ error handling still so confusing to this day? The answer is actually very simple. C++ doesn't make value judgments for you. It never gives you an official correct answer. Should you return an error code or throw an exception? Should you fail immediately when an error occurs or try to continue running? Should you prioritize performance or safety? C++ leaves all these choices to you, to developers and teams. Here are two simple engineering decision references to make it easier for you to apply in practice. First, prioritize error codes for low-level libraries and cross-module interfaces. For example, use enums combined with error message structures instead of bare ints to avoid ambiguous error code meanings. Second, you can use exceptions plus RAI for the business layer and internal module code, especially in resource-intensive scenarios, to reduce the risk of resource leaks. To summarize, there is no silver bullet for C++ error handling. The best one is the one that fits your project scenario. Next time you're struggling with error handling while coding, stop asking which one is correct and start asking, what does my scenario need? Alright, that's all for today's content. What error handling method do you use in your projects? Have you encountered any particularly tricky situations? Feel free to leave a comment below to discuss. If you found today's content useful, don't forget to like and subscribe. See you in the next video.